some problems on complex numbers. Suppose the very first one problem is like that. Find, already we know about the modulus of any complex number. So the question is find the modulus of, first of all, one question is suppose 5 minus 12 I to the power 3, not I, that is I to the power 3. And suppose another one question that is like also same, the modulus of 1 plus I divided by 1 minus I, and also minus of 1 minus I, 1 plus I. So let's start with the first one. As we have 5 minus 12 I cube. So we are writing it 5 minus 12 I cube. Now I cube can be written as 5 minus 12 into I cube can be written as I square into I. I square means it is minus 1. So 5 minus 12 into minus 1 into I. Or we can write it as 5 plus 12 I. So the 5 minus 12 I cube is now becoming 5 plus 12 I. So we have the modulus of 5 plus 12 I. That one is equal to square root of a plus bi. Suppose a plus bi, its modulus can be written as square root of a square plus b square. So we can write it as 5 square plus 12 square, or that one is 25 plus 144, or square root of 169, or that one is 30, and it is always plus as it is only the distance. So it is always plus. So that is the modulus of the first problem. Second one, 1 plus I, 1 minus I, minus 1 minus I, 1 plus I. We are subtracting as normal, how to solve the fractional subtraction like that. So we are taking the denominator 1 minus I into 1 plus I. So that one is now becoming 1 plus I whole square minus 1 minus I whole square. Okay. Now the first one in the numerator is the a plus b whole square. So we are writing it. We are expanding it. 1 plus 2I plus I square. At that moment, I am writing as I square minus 1 minus 2I plus I square. And that one, a minus b into a plus b. So a square minus b square. That means 1 minus I square. So 1 plus 2y plus I square minus 1 plus 2y minus I square. And that one, 1 minus of minus 1, which is originally becoming 1 plus 1. So originally becoming 2. Now you can subtract 1, subtract I square. So it is becoming now the calculation as 4I divided by 2, or simply you can write it as 2I. So that is yet now whatever we have found now, that is how we can simplify the complex number, but we have to find out the modulus. So that means we have to find out the modulus of 2i, which can be written as 0 plus 2i. Okay, so that one is equal to square root of 0 square plus 2 square, or simply 2 is the modulus of that particular complex number. Find the solution of the equation. The equation given like 1 minus I, its modulus whole to the power x is equal to 2 to the power x. So that means we have to mainly find out the value of x. So let's start with the 1 minus I, its modulus whole to the power x is equal to 2 to the power x. Then find the modulus at first. So we can write out 1 minus I, that means originally 1 into I. So we can write it as 1 square plus, that is minus 1 square, its whole to the power x is equal to 2 to the power x, or that is 1 square plus 1 square whole to the power x is equal to 2 to the power x, or that one is 1 plus 1, that means square root of 2, its whole to the power x is equal to 2 to the power x. Now we can write square root of 2, that means 2 to the power half, its whole to the power x is equal to 2 to the power x, or a to the power b whole to the power c can be written as a to the power b into c. In the same way, the property of index, we can write it as 2 to the power x by 2, the left hand side, and the right hand side is as usual, which was, that is 2 to the power x. Now we are dividing, that means we can write 2 to the power x, the right hand side is now left hand side and the left hand side is now right hand side, suppose, for your easy. So 2 to the power x is equal to 2 to the power x by 2. Now we are dividing in that way. 2 to the power x, the right hand side is now dividing in that way. So the right hand side now is becoming 1. That means nothing. We are doing, if a is equal to b, then a by b is equal to 1 in that way. Okay. Once again, we know that if we have a to the power b by a to the power c, that can be written as a to the power b minus c. So here it can be written as x minus x by 2 is equal to 1. So we have here, that is x minus x by 2 is equal to 2 to the power x by 2 is equal to 1, and 1 means 2 to the power 0. So comparing the indices, that means index, it has the 2 to the power x by 2, the base is 2, its base is also 2. So we can write out x by 2 is equal to 0, or x is equal to 0 into 2, or simply 0. So we have x equal to 0. That is the required solution of x. Next problem, show that the points representing the complex numbers. That means here the three complex numbers has been given. That is 3 plus 3y. That is the first one. Second one, minus 3 minus 3i. And the third one, minus 3 root 3 plus 3 root 3i on the Argand plane already described on the previous class. Argand plane are the vertices of an equilateral triangle. Now, when we are discussing about the Argand plane and its position of any complex number, once again I am describing in that way. Suppose that is our imaginary axis, that x is originally our real axis. Now suppose the first one point is representing here, that is 3 plus 3i. Second one, minus 3 minus 3i, means both are negative. So maybe its position is here. So that is 3 plus 3i, that is minus 3 minus 3i. And third one is on the left hand side, the x, but the right hand side is off. Suppose another one point is here, that is minus 3 of root 3 plus 3 of root 3i. What is happening here? Now, 3 points are forming a triangle originally. And we have to prove that 3 points which are forming the triangle is an equilateral triangle. Equilateral triangle means from that point to that point the distance, from that point to that point the distance, and from that point to that point the distance, all the distances are equal. That's why we can say it's an equilateral triangle. That is originally the problem. Now, before we start the problem, once again, we can discuss another one theorem. How should we find the, practically the theorem says, if Z1 and Z2, that means these are those are two complex numbers, are complex numbers of 2 points such as A and B on the Argand plane, as like here, then the distance between them is given by, that means AB, the distance is equal to modulus of Z1 minus Z2. That is the easiest way to find out the distance between two complex number. And how? Let we have Z1 is equal to x1 plus I y1 and Z2 is equal to x2 plus I y2. Then these numbers on the Argand plane or diagram, on the Argand plane, be represented by A, that is our Z1, and B, that is our Z2. That means simply we can say, if that is our point A, that means x1 comma y1 according to Cartesian, and B, that is x2 plus iy2, that means x2 comma y2, that is according to the ordered pair. So how to find out the normal distance between 2 points? If the points are x1 y1 and x2 y2, so we can write AB as square root of x2 minus x1 whole square plus y2 minus y1 whole square. That is the normal distance between 2 points. Then we are proceeding with the complex number. That means here we are proceeding with, suppose, z2 minus z1. We are subtracting the complex numbers. So x2 plus iy2 minus x1 plus iy1, or x2 minus x1 and minus, no sorry, that is plus I of plus I into y2 minus y1. So look at the x, that means the real part, the coefficient of the imaginary part. So if we proceed with its modulus, that means z2 minus z1, we have square root of x2 minus x1 whole square plus y2 minus y1 whole square. Once again, I am saying if we have modulus of x plus y, we can write it as x square plus y square. So that one is our x, that one is our y. Now look at the two values. That is our distance in Cartesian coordinate, and that is the same value, distance, and the value between the modulus of z2 minus z1. So simply that's why we can say that one is the AB or the distance. So how simply we can find out the distance between two complex points, number points? Simply that one is the result, modulus of z2 minus z1. So here, proceed with the main problem. Show that the points representing the complex numbers 3 plus 3i minus 3 minus 3i minus 3 root 3 plus 3 root 3i on the Argand plane at the vertices of an equilateral triangle. Let we are representing the 3 points here. First one is an A, suppose that one. Second one as B, suppose here, and third one as C, so here. So we can find out the values of AB, BC and CA, and if all are equal, then we can say this one is an equilateral triangle. So find out. Okay, so the main problem, we are finding AB. Okay, now A means as z1 minus z2 modulus or z2 minus z1, both are same. So here we are subtracting, that is 3 plus 3i minus 3 minus 3i. Once again look the points, 3 plus 3i minus 3 minus 3i. So we are finding the value of A, B. At first calculate it. It would be better. That one, 3 minus of minus 3, that means 6, and plus 3i minus of minus 3i, that means plus 6i. So modulus of 6 plus 6i, that means square root of 6 square plus 6 square, or square root of 36 plus 36, that means 72, which can be written as 6 root 2. Okay, so that is the value of distance between A and B. Let's check with the second one. That means BC. Which one was our B? That one was our A, that one was B. So we are writing here -3 minus 3I minus 3 root 3 plus 3 root 3I. Okay. So -3 root 3 plus 3 root 3I. So at first calculate the inner portion. That means -3 plus of 3 root 3, that is the real part, and -3I and minus of 3 root 3I, that is the imaginary parts. So that means it can be written as 3 of 3 of root 3 minus 1. Okay, it's better. And here if we consider the minus I, that means 3 plus root, no sorry, I 3 plus root 3, which can once again be written as root 3 minus 1 minus I of 3 of also root 3 plus 1. Okay, so that is our derived complex number. So we can find out the modulus now. That is 3 squared, that means 9 into root 3 minus 1 whole square, and plus here the part is that one and that one. That is our real part, that is the coefficient of the imaginary part. So that one is now 9 into root 3 plus 1 whole square. Okay, so calculate it. 9 into root 3 whole square, that means 3, minus 2 root 3 plus 1 plus 9 into root 3 whole square, that means 3 plus 2 root 3 plus 1. Okay, so if we take the common of 9, 3 minus 2 root 3 plus 1 plus 3 plus 2 root 3 plus 1. So here 2 root 3's are already subtracted. So that one is now becoming 9 into 3 plus 1, 4 plus 4, 8. That means square root of 72 or 6 root 2. So already we have found AB is equal to BC. So final one we have to find out, that one is the AC. Okay, and A means we have 3 plus 3I minus of 3 root 3 plus 3 root 3I. Okay, so if we calculate it, that one is becoming here minus of minus plus, so we can take the common as 1 plus root 3, and here also we can take common the plus I3, that is 1 minus root 3. Okay, so from the real part and also the coefficient of the imaginary part, we can write out 9 of 1 plus root 3 whole square plus 9 of 1 minus root 3 whole square. Now the calculation is the same as previous one, the same as like here. So already we are getting the result here, that is square root of 72 or 6 of root 2. So simply from that particular diagram, we can say the values are, that one is 6 root 2, that one is 6 root 2, that one is the 6 root 2. So simply we can say the triangle formed by the complex numbers on Argand plane by A, B, C is an equilateral triangle. Final one, another one problem. Suppose that there is the same type problem. Here the question is like that: if Z1, Z2, Z3 are three complex numbers such that there exists a complex number Z with the relation given. Which one the relation given? Now Z1 minus Z, its modulus is equal to Z2 minus Z, its modulus is equal to Z3 minus Z, its modulus. We have to show that Z1, Z2, Z3 lie on a circle in the Argand diagram. Practically, what is happening here? We have three complex numbers. Okay, so at first, suppose we have a circle. I am just explaining it with the circular portion. Suppose that is the position of Z1. Whatever or what may be the Argand plane is. That is our X, that is our real axis, that is our Y, that is our imaginary axis. Okay, suppose another one point is Z2 here, another one point Z3 here. Now there exists a complex number Z. Suppose we are thinking the point Z, complex number Z is here. Now if we draw the distance between Z and Z1, then the value is originally Z1 minus Z, its modulus. Okay, if we draw the distance between Z and Z2, then its distance is modulus of Z2 minus Z. And another one, the distance between Z3 and Z is like that one. So here Z3 minus Z. Now look at the relation given. Modulus of Z1 minus Z is equal to modulus of Z2 minus Z is equal to Z3 minus Z, which are practically representing nothing, the radius or the radii of 3 graph. So how to simply, the diagram simply describe that, okay, that is true. That is true. But how to write it? Okay. So we can write it in that way. Suppose that is our point P, that is our point P, that is A, that is B, that is C. So we can write PA is equal to modulus of Z1 minus Z, PB is equal to Z2 minus Z modulus, and PC is equal to Z3 minus Z. As we have Z1 minus Z is equal to Z2 minus Z is equal to Z3 minus Z. So these are representing the radii of a circle with P as the center, and hence A, B, C lie on the circumference of the circle. Simply the diagram defines all the things.